So let me go through from the top here what it was we did in order to work on finding the acceleration from a position graph. First of all, we had to take this data, and I'm going to go from the top here, and then we're going to go to our graphing calculator and go through again. Then we're going to go through again this problem, but we're just going to do it on the graph. Sorry, I got distracted. Let me go through the top here, what we did on paper, then I'm going to go through from the top what we did with our graphing calculator, and we'll finish it off. So when you construct a position time graph here, we discover that it is a curve. And if I want to find the acceleration, you need to pay attention to the words here. This is a position graph. If I want to find the acceleration, then what we have learned is that from a graph you can find acceleration as the slope as long as it's a velocity graph. Okay? So we're trying to construct a velocity graph from our position graph. And what the reasoning was since the position graph looked like this, and velocity is the slope of this graph, we had to find the slope of this graph at a number of different points. And that was where it got very confusing, because you had to draw those tangent lines. And we constructed from that position graph, we ended up constructing, let me get them, these velocities. Remember doing that? And then if we plot those velocities on our velocity graph, we end up getting a straight line, and our goal was to find the acceleration, so we find the slope of that line. Okay. I want to make something very clear to you here. What we're doing in this whole example is not something that you would be expected to do on an exam. We're doing this to explain and to learn the properties of graphs and how you could take experimental data and turn it into an acceleration. So we ended up getting an acceleration of, I got 19 meters per second squared. I think Ashland got 18, somebody else got 22, I saw. But then what we said is, instead of doing that, and this is where I want you to really focus, we could put this data into our calculator, and I think I still have my data in here. I do. We could put the data into the calculator. We could turn our stat plot on, set up our window settings to show this data. D, which is on the y-axis, goes from 0 to about 200. And T, which is on the x-axis, goes from 0 to about 5. And we can look at the data. It looks like that. I'm just curious, does anybody remember what we call this shape? It's not linear. I used a different word. Quadratic. That's right. Have you taken 20-1 in math yet? Okay, you're going to study a lot of quadratic graphs and equations in that course. So now what we can do is go to our stat calc and do not a linear, a quadratic regression of the data. So before, when we had data, and you're going to do a linear regression for your lab because your lab is linear. Before, when we had data and it was linear, you did linear regression. Here we go quadratic regression, and it gives us an equation. The equation is y equals ax squared plus bx plus c, where a is 9. So right at the end of yesterday's class, somebody said, well, wait a minute, how did we get that graph to now graph it? I think you were talking about that. Now that we know it's y equals 9x squared, we can go into y and put 9x squared. And if I graph this, not only can I see my data, but I can see that my graphing calculator did a phenomenal job of finding an equation of a line that matches that data. And that's where we ended yesterday. Now, don't forget what we are trying to do here is find the speeds at these points in time. So now I'm going to show you how we can find them on the calculator. Once we've done all of that, the first thing you want to do is turn off your stat plot. It served its purpose. The only reason you do a stat plot is to see the shape so you know what type of regression to do. Once you have the equation, you don't need to worry about those data points anymore. And then what you're going to do is go back to your graph. So this is the graph. And we want to find the slope of the tangent at 1 second. Remember I drew that straight line at 1 second and I found the slope to be 18.3? Well, there's a way to tell the calculator to find the slope of the tangent. You go to your calculate menu, which is second trace, and I wish I could explain to you why it's this set of symbols, but I can't. It's a calculate thing. Do you see it kind of looks like delta y over delta x? Kind of. Think of that as slope. So when I choose that option, and then I enter the x value of 1 second and hit equals, I get 18. It's telling me the slope at that point is 18. I did pretty good. I got 18.3. That surprises me. So from our calculator, we get 18. Let's do the same thing for 2 seconds. I go to my calculate menu. I choose this because it calculates the slope. I put 2 seconds and I get 36. Again, not too shabby, as my dad would say. I got 38, it's actually 36. We can do it at 3. Bless you. We can do it at 3 and get 54. We can do it at 4 and get 72. So now we know the speeds. Keep in mind, I can do everything I've just described to you today, finding the speeds, without putting my pencil to paper one time. I don't even need to do the distance graph. It was all done on my calculator. Now think about what we did next. What we did next is we plotted those speeds on a velocity speed graph. I don't need to do that. I can put them in my calculator in list 1 and 2. Or I can put them in 3 and 4. It doesn't really matter. But I don't want to add to what I know is already a confusing topic. So I'm going to go back to my list. So stat, enter. I might as well clear them all. Go back to my lists and put in 1 second. Put in L1. Where am I here? There we go. Put in for L1, 1, 2, 3, and 4 seconds. Put in for L2, 18 meters per second, 36 meters per second, 54 meters per second, 72 meters per second. And look at the graph on my calculator. I'm hoping that if we do this kind of procedure with the lists and the graphs and the equations on the calculator enough times, it'll sink in. So what's involved in looking at the graph of this data? Two things. I have to turn the stat plot on, and I have to adjust my window settings to see that data. My time goes from 0 to basically 5. My speeds, these are speeds now, not distances, goes from 0 basically to, I'm going to go 85. So I've entered my speeds and times in L1 and L2, well, L2 and L1. I've turned my stat plot on, I've set up my window settings. Boom. Does that look linear to you? Does it look like it's, oh, not that. Let's get rid of that. That's the old equation. Does the data look linear to you? That's another thing I should have said we do. You turn the stat plot on, set up your window settings, and go into Y and clear out anything you've graphed. Does it look linear? Okay, then what type of regression do we need to do to find the equation? Linear. Go stat calc, linear regression. The equation is y equals 18x. Well, the slope is 18 then, right? But the slope is the acceleration. Let me back up and do that again. Does yours show something different?
Yes.
Can you show me what it shows? Well, that's pretty weird. I'm baffled. 118, 236, 3, oh, look at your last entry. So when you, I'll just explain what's happened. The 72 was entered as 76. That little change moves that last data point to a different position, and when your calculator draws or finds the regression equation, it tilts the line up a bit to try to reach that point. You're good now? Okay, so the slope is 18. That means the acceleration is 18 meters per second squared. So from the top, and again, this is not something you are going to be expected to do on an exam, but I would like everybody to turn to page 16 of your unit handout. And what we are going to do is is the example or the assignment problem on page 16, all on the calculator. Okay? What we are trying to do here is basically determine the acceleration for the data on page 16. Is this the data? No, I didn't think so. Come on. There we go. This is the data, right? And it says we want to determine the acceleration of the object, and if you flip a couple of page over, one page over, you can see what the answer is, can't you? at the bottom. It says 25 meters per second squared. So think about this for a second. If you did this on paper, it's a nightmare. You'd have to construct this graph, draw a whole bunch of tangent lines to find a whole bunch of speeds, plot the speed graph as a function of time, find the slope. We're on our calculator here. So the first thing we're doing is going to construct a position graph on our calculator. We need to clear all of our lists. Go stat, enter to get in there, and enter 0.5, 1, etc. So I've entered all of my times in my data table. They start at 0.5, and then 1, 1.52, 2.53, 3.54. My distances or positions, 3.1, 12.5, 28.1, 50, 78.1, 112.5, 153.1, and 200. For the exact reason that you encountered, it's why I always say double check all of your entries here before you go on. I guess not always, because I didn't say it last time. So we want to make sure these are all right. 200, 153.1, 112.5, that's good. 50 is good. 28.1 is good. Good. So listen carefully. We want to do a regression to find the equation that describes this data, but before we do a regression, we have to know what it looks like. Because if it's a straight line, we're going to do a linear regression. If it's not a straight line, we have to do a different regression. So what do? I go into y equals and I clear out anything in there. I turn my stat plot on, and it's still on from last time. I set up my window settings to reflect the data table. So I go from 0 to 4 seconds. So 0 to 5 is good enough. Let's face it, I just want to see what this looks like. I don't need a perfect window setting. And it goes up to 200. I mean, I can go 210, 225 if you like. Graph. So you should be recognizing this curve, everybody, as accelerated motion for a position time graph. And the reason is because it goes from this steep to this steep to this steep to this steep. And the steepness, which is the slope, is the speed or velocity, so the velocity is increasing. That's accelerated motion. Before we go on, I just want to save that, because I might refer to it later. So this is the position graph, and it shows accelerated motion. If we want a velocity graph, then we need to get some velocities from this. But velocity is the slope of that graph on the left, and to find the slope on paper is a nightmare, right? So what we're going to do is find the equation of this, so we can graph it on the calculator to tell the calculator to find the slope at different points. I'm going to do a regression to this equation, or to this data. So I go stat calc. It's going to be a quadratic regression. You'll probably notice there's lots of regressions. Linear, quadratic, cubic, quartic. There's sine, log, logistic, all kinds of weird things. So I do that, and I get this equation. Let's talk about this just for a second. This is saying y equals ax squared plus bx plus c, and it's telling you a is 12.5, b is 0.002, c is negative 0.018. So what I want to do is go into y equals and enter that equation. Now, if you have a TI-84, let me show this to you. New. Open. Ooh. If you have an 84, and it's going to take me just a minute to get my data in there. Thank you. If you have an 84, when you go to your stat calc, whoops, and you do the quadratic regression, you have options, okay? And normally you just kind of keep hitting enter, enter. But when you get to store regression equation, you can put y1 there, so when I finish, it will do its work and it will put that whole equation in for y1. y1 is a variable, so you go to your vars section. It's a y variable, so you scroll over. It's a function, so you hit enter. It's a bit of a mess to get to, but now it's going to store my equation as y1, and I don't need to write all this down and then type it in. There's a way to do it with the 84 as well, but we won't worry about it, okay? Right now. I'll show you in a bit. So I go calculate, calculates the equation, but look at the beautiful thing here. Shows the equation. Now I'm going to set up my window settings so that it matches what you've already put in there. I'm going to turn my stat plot on this calculator. So does the curve match the data? Yep. You can turn the data off now because you don't need it anymore. So go back to your stat plot and turn it off. And now you're going to find the speed of the object at a few places so you can plot a speed graph. Essentially what we're going to do is create a table of values now for speed at various times. I would recommend 1, 2, 3, 4 seconds. I go to my calculate menu, second trace, choose option 6, put in 1 second. The speed at that point in time is 25. Basically. I do the same thing at 2 seconds. The speed is 50, approximately. So can you continue with this process and find the speed at 3 and at 4 seconds? Pardon me? So if you do not have a TI-84 and you have a TI-83, you're at this stage, right? But you need the equation in there, so you need to, on the TI-83, go y equals and type this in. Okay. Would you like me to show you how we can just tell the calculator to grab that equation and put it in on its own? Okay. So the first thing to note is you have to have just completed the regression. It has to basically be the last regression you did. You go to y, and you can either type this in, or you can go to vars, down to statistics, because that's where regressions happen, over to equation, because we're looking for a statistical equation, and choose regression equation. And watch what happens. Well, you can see it on your own calculator. I do that, it puts it in. Okay. It's just that with the TI-84 or higher, you can tell the calculator to do that at the same time that it's doing the calculation. Do you agree you get 75 meters per second and 100 meters per second, basically? How many of you understand that the slope of this graph will be 25? If you want to now put this in for L1, this in for L2, and do a linear regression to find the slope of that line, that's up to you. But you'll get 25. And in the time that it would normally take us 45 minutes or so to do those graphs and do the slope with the tangent lines that we draw that are not drawn perfectly and get an answer that's not great, in that 45 minutes, we could do it in 10 minutes on our calculator. Once again, I want to highlight to everybody, you are not going to be expected to do any of this on paper. I go through this whole exercise with you to get you more and more familiar with your calculator and to get you basically familiar, everybody, with this idea. Let me go back. That if you have a graph like this for position time, you are going to have a graph like this for velocity time, and the slope of that line will be the acceleration. All right, we're going to move on. We're going to take a look at the next lesson now. And now we're starting to settle back into a good routine. We're going to learn some stuff today. You're going to practice some stuff on your own. I believe this is on page 18 of your handout. We're going to be doing a couple of things today. We're going to be analyzing velocity time graphs, which is essentially finding displacements and accelerations from velocity time graphs. We're not constructing velocity time graphs. They're going to be given to you, and you have to find information from them. And the second thing we're going to be doing is calculating what we call average velocities and average speeds. So there's really two layers to this lesson. You already know that the slope of a velocity time graph is going to give you the acceleration of an object. That you should know that. There's something else you can find from a velocity time graph, and that's displacement. So somehow in a velocity time graph, displacement information is given. And these examples are going to illustrate how we find how we find displacement from these graphs. So take a look at the first graph. A flight leaves the airport and flies at 300 kilometers per hour. After 2 hours, the flight turns around and makes an emergency landing. So what is the displacement during the total 2.5 hours? Now, let's read this graph first of all and understand what's going on. The vertical axis is velocity. So for the first 2.0 hours, there's a decimal in there, the plane is flying at positive 300 kilometers per hour. It's flying east at 300 kilometers per hour. something happens. It's on an 8-hour flight, but something happens. The landing gear isn't operating well, or there's a loss of pressure in one of the sections of the plane. So rather than continuing to their destination, they turn around and they go back and they land someplace else at a different airport. Not one that they started at, but a different one, because there's an airport they just passed a half hour ago. So they turn around and they fly at 300 kilometers per hour in the opposite direction. I think everybody's aware there's something a little goofy with this graph. You can't go from flying 300 kilometers per hour in one direction to instantaneously flying 300 in the other. Okay? There's got to be a slowing down in that direction and a changing direction, or a general change in direction. Look, sometimes particularly in high school, science and math, science mostly, you oversimplify things to the point where they're not really possible so that you can learn. Because if I said we're going to take into account that big looping turn, I can't really explain to you what you need to know here. It's too complicated. So the first thing I want us to do is I would like everybody to find the displacement, the change in the position in the first 2 hours. What is it equal to? Let's see. Well, we know that velocity is displacement over time. It's change in position over time. That's a formula given to you on your formula sheet. Have I given you a formula sheet yet?
Yes.
Yellow formula sheet? Can you get it out? You don't have one? I think I must have, because I don't have a whole lot left, but if you need a formula sheet, please let me know. So I would like you to look on the side of the equation that has, the side of the formula sheet that has all your equations, and I'm asking this question. Is this formula that I've written on your formula sheet in the kinematic section? Is it? I'm a person of precision. It's not there, because what's there is V average. Okay? I'm going to be pointing that out to you a number of times throughout the semester. We want to make sure we understand the difference between average and instantaneous. But what I will tell you is, since looking at the graph, the velocity in the 2 hours is constant, the average speed in the 2 hours is 300. So sometimes, even though it doesn't say average in what we do, we don't need to include it, even though it's on the formula sheet. This is a very simple calculation. If I put 300 kilometers per hour equals the displacement, which is the change in the position, over the time, which is 2 hours, this is almost like stealing candy from a baby. In fact, I would just say to you, I don't know that you really need the deltas. And when you multiply both sides of this equation by time, you get speed times time equals distance. I guess I should explain this now. When you take a look at what I've written here that I'm going to highlight in blue, that is what you would put for a written response question. You've put the substitution in, you've got the units. I know that your Science 10 teachers probably really harped on you need units, right? But over the next few days, you're going to discover that what I will be doing is simply saying this. Because when the equations get more complicated, and you can look at some of those kinematics equations that we're going to be learning, when they get more complicated, can you imagine what it's going to look like when you start putting units everywhere? It's going to get confusing. So I think this just makes it simpler. I can see that if I multiply both sides by 2, I get D. If you want to do the cross multiplying thing, that's fine. How many of you have been taught by a math teacher for cross multiplication, some kind of fish thing. Try to unlearn that, or try to learn a different way to think of it, because it's going to let you down. In Math 20-1, it will really start to let you down. Anyway, do you agree it's 600 kilometers? Okay. Can you do me a favor, please? I think I can get rid of that. And find how far it travels in this 1 hour. It's not a difficult calculation. Or is it a half hour? It's a half hour. 150. Right? Distance equals speed times time. So distance equals 300 kilometers per hour multiplied by a half an hour. This is 150 meters. But I did all my calculations and discussion in terms of distance, but we're asked for the displacement. And since it was traveling in a positive direction for the first 2 hours and a negative direction in the next half hour, the two displacements are 650, positive 650, and negative 150. Are you with me? Total displacement. The total displacement, change in position, is 600 meters, is 600 kilometers plus negative 150 kilometers, which is 450 kilometers. And this is a very, very simple question. I mean, all you're doing is you're reading the information off of the graph. Now, what if we take a look at the second example, determine the total displacement during the 10 minutes. That's pretty weird. Let's do this in pieces. I would like everybody to determine the displacement in the first 4 seconds. It's moving at 6 meters per second for 4 seconds. This is not a difficult calculation. What am I going to do? I'm going to put the units here just to show you why we get meters, but that should be very basic. The seconds cancel. Would you agree? So in the first 4 seconds, it travels 24 meters. I would like everybody to calculate the displacement from 5 seconds to 10 seconds. So I'm not interested in how far it travels in this 1 second interval here. I'm interested in the third section. And you can see that it's 2 meters per second multiplied by 1, 2, 3, 4, 5 seconds, which gives us 10 meters. So far what we have here, everybody, is in the first 4 seconds, it travels 24 meters east. In the last 5 seconds, it travels 10 meters east, but it also travels a further displacement in between. Well, I talked about that formula having average with the velocity for a reason. Let's talk about that now. V average equals, can you support me when I just say, let's forget about the deltas and let's forget about the vectors and just say distance over time is speed. If we need directions and deltas, we can talk about them, put them in. I would like everybody to think very carefully about this next question. From 4 to 5 seconds, we're trying to determine, everybody, the area, not the area, whoops. We're trying to determine the distance traveled in here. I would like everybody to try to find or figure out what you believe the average speed is in that 1 second interval. And when you think you know the average speed, just put your hand up and then down. Because if you look at the beginning of the interval, it's traveling at 6 meters per second. If you look at the end of the interval, it's only traveling at 2 meters per second. It doesn't travel at 6 meters per second the whole time. It doesn't travel at 2 meters per second the whole time. I'm asking you, what do you think the average is? And I hope, as I said that, a few more people, you kind of said, oh, yeah, I get it now. What do you think the average speed is? 4. It's halfway between the 2 and the 6. Only because it's a straight line. You will never see something that's not a straight line in this context. So in this region, the average speed is 4 meters per second. So if we multiply that by the 1 second, we get the displacement, and you get 4 meters. You with me? So that means it's 4 meters here, and we can answer the question. 24 plus 4 plus 10 gives me 38. Okay. The answer to the question is 38 meters east. But finding that average speed is not always going to be easy. So I want everybody to do the following. I would like you to look at the shape. I'm going to erase everything. I already have it saved on a different page. There it is. I would like you to look at this shape that I'm going to highlight. In pink. And imagine that you're in a junior high or elementary school math class where you have to find the area of that shape. Your teacher, if your teacher was on the ball, would say, you know what we can do? We can break that into a rectangle and a triangle. Because you know how to find the area of a rectangle, right? It's length times width. So I would like everybody to find the area of this. It is 1 second this way and 2 meters per second that way. The length and the width have units. So when you multiply 2 meters per second by 1 second, what do you get for the area? 2. This area is 2. And it's 2 meters, because when you multiply the dimensions, you get meters. I would like us to calculate the area of that triangle. So how do you calculate the area of a triangle? Base times height over 2. By the way, that's on your formula sheet. Believe it or not, the area of a rectangle and the area of a triangle are on your formula sheet. There's a section called Trigonometry and Geometry, and it has area of a rectangle, area of a triangle, area of a circle. It also has circumference. So base times height over 2. This was length times width up here. This was 2 times 1. That's where we got the 2 from. This will be, let's see, the base is 1. Well, I'm going to go 1/2 base times height. You okay with that? 1/2 base times height? 1/2 times the base, which is 1, times the height. What's the height of that? 4. This gives us 2, which is meters, because we multiplied meters per second by seconds. So what's the total area of that shape? The displacement is the area. You don't need to try to figure out an average velocity. You just break it into shapes that you can calculate the area of. And had I said to you, everybody, find the area. I better use this one. Find this area. You would have broken it into the rectangle, the rectangle, the rectangle, and the triangle, and you calculate all of those areas and add them up. That's how we find displacement. The lesson to be learned here, and I really believe you need to write this down somewhere, is if you have a velocity time graph, the area equals the displacement. And if you had a section of the graph that was below the time axis, then that's a negative displacement. I mean, just look at the first example. Here's an area between the time axis and the graph. Here's an area between the time axis and the graph. They're both rectangles, but if the rectangular area or the area is above the axis, it's a positive area. If it's below, it's negative. Those of you that will eventually take calculus with me next year will learn that we talk about negative areas all the time in terms of graphs. All right, we still have one more thing to do. We were also asked here to determine the acceleration during each of the 3 parts of the trip. So what is the acceleration? Oops. What is the acceleration here? What is the acceleration here? And what is the acceleration here? Well, how do we do that? We learned yesterday acceleration is going to be the slope of a velocity time graph. So what is the slope of the first section of the graph? 0. What is the slope of the third section? 0. What is the slope of the middle section? Well, rise over run. Now, I mean, I can't teach everything, but sometimes I really wish that if anybody who teaches Physics 20 teaches those students Math 20 first, or you've had me as a math teacher before. But none of you, I don't think, have had, well, a couple of you have had me as a math teacher. When you think of the concept of slope and rise and run, it's very useful to always say run is always to the right and then there's a rise. So when we start at the beginning, we say there is a run and then there is a rise. The run is always to the right. So the question is, how far to the right does this arrow point? Well, it points 1 to the right. So the run is 1 second. And what is the rise here? Everybody think about what the rise is. Do you know, Nate? -4 what? Not meters. Look at the graph. You know, Jay? Right, -4, because it's 4, negative means it's down, and it's meters per second. So you've got to look at the units of the graph. -4 meters per second, which means it's -4 meters per second squared, because -4 divided by 1 is -4. I told you at the beginning of this lesson that we're doing 2 things. Analyzing velocity time graphs. We've now finished that. With a velocity time graph, area is displacement, slope is acceleration. So when I said you should probably write this down, we can include that statement. If you compare that to a position time graph, it doesn't matter what it looks like, just like it doesn't matter what that velocity graph looks like. Those things are true. The only thing we can really say here is that the slope equals velocity. That's the only information you can get from a position time graph is velocity. If you want to know acceleration from a position graph, then you need to get velocities from it to create a velocity graph. All right, now we have one more example to cover, and it deals with the second thing I said that we were going to be learning in this lesson. The second thing I said we were going to be learning is what's highlighted in green, calculating average velocities. Let me ask you a question. If you had a Physics 20 class from me, and for some reason all you did was write one quiz and the final exam, okay? And I exempted you from everything else because you were ill. You were here on the first day, you wrote a quiz, you were really ill, you were in the hospital, you came back the day before the final exam, and I said, well, man, there's nothing I can really do. And you said, you know, but I've been studying, can I write the final exam? Are you with me? And you get you had 100% on the quiz, and you get 10% on the final exam because you were so confident you knew the material, but really not being in class, it's almost impossible. Can you average those numbers for me? Can you find the average between 10 and 110, or 100? It's 55, isn't it? 100 plus 10 equals 110 divided by 2. I'm not going to give you 55% because the final exam is worth more. Are you with me? You're going to fail the class. So now imagine that we had this situation. And again, the graph I'm going to give you is not a very realistic graph. But you have velocity and time, and we want to find the average velocity. And for part of the trip, you're traveling at 20 meters per second. And for part of the trip, you're traveling at 40 meters per second. I'm really asking you to think. I'm challenging you here. Can somebody explain why I don't know whether the average is going to be 30 or not? Yeah? Right. It might be this. In which case, I hope everybody would agree that up to this point, my average velocity is going to be a lot closer to 20 than it is to 40. Or, if it were like this, then my average velocity is going to be a lot closer to 40. And I know that many of you, if you knew those times, you could maybe figure out the average velocity as kind of a puzzle. But there's a very definitive way to do it, which is what this example is about. So for an object whose velocity changes, you can find average velocity or average speed. So let's take a look at this one. A student jogs 750 meters east in 6 minutes, stands there for 10 minutes, runs another 2 kilometers east in 11 minutes, then turns around and walks 1 kilometer west in 20 minutes. What is the average speed of the student? Okay. So I'm going to give you a different variation of the formula speed equals distance over time. Average speed is total distance over time. You just add up all the distances and you divide by the time. That's all. Like when you look at this, let's add this up. 750 meters plus, what else do we got? Oh, 2,000 meters. 2 kilometers is 2,000 meters plus another 1,000 meters. You guys will correct me if I'm wrong, I hope, but I get 3,750 meters. Okay. That's the total distance. The total time is 6 minutes plus 10 minutes plus 11 minutes plus 20 minutes. So the total time, and again, correct me if I'm wrong, what do we got? 30, 47 minutes. Okay. By the way, there's absolutely nothing wrong with units of meters per minute, but we don't like that. We would rather have kilometers per hour or meters per second. So I'm going to go meters per second. That means I need to multiply this by 60. Uh, 2820? Yeah. Anybody else? 2820? Pretty sure. So 2820. You'll notice here I don't really care about the units here. You're really multiplying by 60 seconds per minute, but who cares? Some of these things you're taught in Science 10 are just not important. So according to what I've told you, the average speed will be equal to 3,750 meters divided by 2,820 seconds. We're finding a speed here, so speed is a scalar, direction is not important. I get about 1.3 meters per second. What does that mean? It just means that averaged out over the whole trip, that's your average speed. Had you, instead of doing all of these little things for 2,820 seconds, had you instead walked with that speed for the whole time, you would have still walked the total distance. It's just an average. Okay? And lastly, what's the average velocity? Well, what I'm going to tell you here is that we modify our equation so that its average velocity equals total displacement over total time. I hope you see that that is subtly different than what I wrote before for average speed. It's displacement. So now when you add these, that's 750 meters and the 2,000 meters and the 1,000 meters, you have to say I'm going to add 750 meters east, 2,000 meters east, and 1,000 meters west. And we actually started the year off by talking about displacements and adding things together, but now we're starting to really get into it. When I add these together, I want to turn this into something that I don't have to think about the directions. So I translate it into the following. I say to myself that when you look at a map, everyone, imagine a map of Canada. Here's Newfoundland and Labrador. This is Vancouver Island. West is that way. That's to your left. So we say west is negative. And east is that way on a map, which is to your right when you're looking at it, as long as you're looking at the map right side up, right? Maybe you're traveling south and you've got the map turned around, but that's not what I'm talking about. Looking at the map right side up, east is positive and west is negative. This takes all of the thinking out of it. When I add these numbers together, I get positive 1,750, do I not? Meters. And that means that the total displacement is 1,750 meters east. So now I can take the 1,750 meters. Did I get that right? 1,750? Okay, good. And the east is not part of our calculation. It's just kind of hanging on there as a direction of our answer. Divided by the 2,820, and that's in seconds. And you get about 0.62 meters per second. east. What this is telling you is the person did walk east, east, and then west, right? But what this is telling you is instead of doing all that other stuff and stopping in the middle and all that, they started, and for the whole 2,820 seconds, they walked east at 0.62 meters per second. Then at the end of that time, they would be in the same place they landed in had they done it the original way with all those pieces. That's it. And now we're back on track where we can get some practice done. You have textbook questions on page 34 and 37. Let me show them to you. Page 34 and 37. One of them deals with a velocity time graph. Another one deals with a velocity time graph. Then we've got some average velocities and average speeds. And then on page 44, we have more velocity time graphs to deal with. So when you're looking at this, what's the displacement? You learn about rules, like the fish thing in cross multiplying, or about cross multiplying. Or you learn about rules like area of a triangle is 1/2 base times height. So that every time you see a triangle, you don't need to develop the area. You learn about rules to make your life easier in solving problems in the real world. So the rule is, the answer to this question is, find that area. So you can break it into 3 rectangles if you like. You can break it into a large rectangle and then subtract the area of that little piece. But you want to use the rules. You don't want to think of these as puzzles. So that's your assignment for Tuesday. On Tuesday, don't be surprised if there's a little quiz on Tuesday. There may not be. I may be telling you maybe there's a quiz and I'm not planning on having one. I may be telling you that because I really am planning on having one. Okay? Or maybe I'm not. But I might. Okay? By the way, I have to be away on Tuesday, unfortunately. I hate not being here. So regardless of whether there's a quiz or not, the lesson that you're going to be doing Tuesday ramps it up a bit, but I will have a video recording of the lesson. So you'll still be okay. Anyway, get started on those problems. I will, you still have about 25 minutes, 20 minutes or so to work on this, and I'll come around and I'll help you out. Yes, Nate? Of course. Yeah. How many of you do not have a textbook? Well, that really is horrible. No textbooks. Can't afford textbooks? I guess we'll just think about learning. Okay, so what I am going to do is print this out for you, but in the meantime, I'm going to put these questions right here so that you can read them. So you're going to have to give me a minute here to print this stuff.